Okay, here we're going to look at some of the fundamentals of kinematic graphs. First, we'll go over some basic terms. So here we have a position time graph. We can use this to show the difference between distance as opposed to displacement. Distance would be literally the total distance traveled. So the object is, for an example, starting right here. It moves all the way up to here, and then it turns around. Well, if we're talking about distance, that's a scalar quantity. We're going to ignore this turning around and just measure how far it goes from here down to here, add those two together, ignoring the fact the object changed direction, and then add how far it went from here at the bottom all the way to the end. So we would add this term to this term to that term. Add them all up. That would be the distance traveled. You can see from this graph that's not a very useful thing to have because it's hard to calculate even given the graph. Displacement, on the other hand, is just the change in position. So if we want to know the displacement, we would just go from the beginning of the graph to the end of the graph. And the displacement is just this distance right here from beginning to end. It has a vector because we can see that it moved forward, because we're going to include the changes of direction. So displacement can be read straight off from a graph. You just find the final position and you subtract the initial position. Speed and velocity are similar type relationship in that speed is the distance traveled divided by the time taken, and velocity is the displacement divided by the time taken. On this graph, the velocity would be related to the slope of the graph. So this right here would be the average velocity from the beginning to this point. We would take the difference in the positions, which is the displacement, divide that by the difference in the time, and we can see that here we have the average velocity. Now we can distinguish between average and instantaneous. This is an average rate over a long time interval. On the other hand, if we make that time interval smaller and smaller and smaller, eventually it becomes so small that the average velocity becomes the tangent to the curve. And then if the interval of delta t and the limit as it goes to 0, then we get the tangent to the curve, and that we call the instantaneous, in this case, velocity. Acceleration would be the rate at which, in this case, the slope is changing. So right here we have the slope is basically starting large and positive, and then it gets smaller and smaller. Right here, the slope goes to 0, so the velocity is no longer changing. And that is what we mean by the acceleration, the rate at which the slope of the position time graph changes. And we should all know the difference between vectors and scalars. Vectors have plus and minus signs that we interpret as being forward or backward, or as terms of a direction. For scalar, for our purposes in one-dimensional motion, a scalar is just a positive number. So, for example, speed is a scalar because it has no sign. Velocity would be a vector because it has a sign. Now we can look at a graph. Here we have a position graph. We can look at the instantaneous velocity, which is just the slope to the graph right here. And we can use that to graph the velocity graph. So here we can see the slope is getting smaller and smaller and smaller, so the velocity is getting smaller. Right here it goes to 0. Velocity then becomes negative, and right here it again goes to 0. So we would draw on the velocity graph these two key points. Here the velocity is positive, then it's this negative, and then it goes positive again. Now, small point that I found online. One other professor did note that the tangent to the curve right here is what we mean by the average velocity, instantaneous velocity. And if you draw this line right here, that is called the secant to the curve, and that is called the average velocity. That is not something most people draw a distinction on. Now, we can then look at the area under a curve. So here I have a velocity time curve, and if we take this little sliver right here, the width of it is a small time interval. The height is the average velocity during that time interval. We multiply the height by the width, and we get the area of this, which is the speed at which it was traveling times the time during which it was traveling, and that product gives us the area, the distance it traveled during the small little time interval. So if we take all of those and we add them all up, we would get the total displacement from here to here, adding up all of these small little slivers. That is what you're going to end up calling the integration the integral of v dt was the symbol we use for finding this area. Calculus is extremely helpful when this area is not a simple geometric shape, like a triangle or a trapezoid or a square or a rectangle. If it becomes a more arbitrary curve, then finding the area using calculus or just doing it numerically integrating it will be more useful. We're also going to distinguish between area above the curve, which will all be positive area because of positive velocity, as opposed to area under the curve where we have negative velocity. So we're going to call this area in the green up here positive. This area down here in the red we're going to call negative. So the total displacement would be adding a positive area right here and a negative area right here to get the total displacement or change in position from this time to that time. Now we can look at how to draw a graph using a slope. Here we have a velocity time graph, and we have a line right here which is the tangent to the curve. The slope of that is the acceleration, and we can use that slope to graph the acceleration versus time. So what we often want to do first is note right around here the tangent looks pretty horizontal. At that point the acceleration would be 0. So in drawing the acceleration graph, that's where it's going to cross the axis. And here we can see it does that one other time. Way back here, the slope also pretty well goes to 0. And at that point, we go to the acceleration graph, and again, it crosses. Then over here, we can see the velocity is actually slowing down and stopping. So we have it's gaining velocity, it's losing velocity. It's gaining velocity. Whoa. Gaining velocity, so positive acceleration, but that positive acceleration is getting smaller and smaller. So in the acceleration graph, we have a positive acceleration that gets smaller and goes to 0. Then right here, the acceleration is negative because the slope is negative. Right around here, it looks like it reaches a maximum slope. And then after that, the slope gets less negative and closer to 0. So the acceleration curve should get to be a larger maximum a negative acceleration. This is at we call the inflection point. And then it becomes smaller and smaller, and right here it goes to 0. And at the very tail, there's a little bit of more positive acceleration as the slope goes positive down here at the end. So that's the connection between the slope of a curve and graphing its slope. And that's an example using velocity and acceleration. We can also show how we can use the area under a curve to graph, in this case, the velocity from the acceleration. The change in velocity is the area under the acceleration time curve. Here we're going to start with an object at an initial velocity of 3 meters per second. We need to know that because this curve right here will not tell us the initial velocity. It only tells us how the velocity changes. So what we're going to do is find this area. Notice this area is ever increasing because it's a triangle. So every time we add it, we're adding more and more. And up until here, then we're adding a constant amount because we're just adding, now it's a nice flat square rectangle. So when we draw the graph, this is increase at an increasing rate. So here we've got it curving, and then it straightens out because we're adding a constant amount because every one of these squares would have, for the same 1 second, we'd be adding the same amount of velocity. So the slope becomes constant. This right here should be a straight line, and this right here should be a curve because the acceleration is increasing. So this area right here would give us a curve on the velocity graph, and this area right here would give us a straight line on the velocity graph. So that's how you can use the area to basically calculate a graph for the other variable, in this case, a velocity. In class, we will do some more examples. So we'll have a velocity graph right here, and then you can calculate the area under that to do the position graph, and then find the slope of that to get the acceleration graph. And we will also look at some constant acceleration graphs. And I'll give you this data. You can sketch it and then check your answer here. And we will also do some more general examples where we have a velocity graph, find the other two, or have an acceleration graph, find the other two, or a position graph, and find the other two. One other thing I do want to raise is, notice we have one variable, position, of our four basic kinematic variables. The next one is velocity, which is just the first derivative. And then we have the second derivative, which is the acceleration. And the question you might ask is, why don't we continue adding more and more derivatives? Namely, why don't we talk about the derivative of the acceleration or the third derivative of the position? Why don't we usually talk about that? Well, the answer is we actually could. That actually does have a term. It is called a jerk, because that's a sudden change of acceleration or a quick and sharp change in movement. It's often what you feel like you're being jerked around. That's what it means. However, that doesn't have any fundamental significance. The reason for that is when you do experiments, we discover that where you are, your position, is just relative, has no fundamental significance. It doesn't really matter if you're in front of or behind a particular point. Galileo also discovered that all motion or all velocity is relative. There's no fundamental significance to being at rest. You're only ever at rest with respect to a certain frame of reference. So velocity has no fundamental significance. However, Isaac Newton discovered, because all objects in freefall fall at a constant acceleration, the second derivative is related to how objects interact with each other through a process he called applying a force. This is more fundamental. This is not something that in Newtonian mechanics is considered to be relative, because it depends on how objects are interacting with their surroundings by exerting forces on each other. This is the one that has a fundamental significance. The other derivatives do not. And that's why we talk about the first, basically, function and then its first two derivatives.